Hi everyone, my name is Netta and this is Chemistry at Glance. If you haven't been here before, I encourage you to visit my website first when I explain a little bit about myself and what I do here. And if you've already been with me or seen my previous videos, let's just start with this one. Okay, so obviously we're going through the first year of A-level chemistry. So this is AS level chemistry, and today's topic is mass spectra, IR spectra, and carbon-13 and hydrogen NMR spectra. I have prepared many different past papers for you for this topic, but if you want any past papers for any other topic on AS level spec, I have many more videos prepared for you. Okay, so some of you may be thinking, whoa, what's all about these questions if I haven't even revised this topic yet? So if you haven't revised it, just visit my website and I explain this topic thoroughly in there. So everything you need to know about it is in my blog. I leave all the links in the description box below, so just click on it and it will transfer you right to the website. Okay, so these are some of the first questions I prepared for you, so let's just start with the first one. So we have to complete the following sentences. So in a mass spectrometer, something ions are produced. So something to know about mass spectrometer. There are a couple of stages you need to be able to explain. There is also a graph you have to be familiar with. But what happens mainly in the mass spectrometer is you have these atoms, or compounds rather, they are inserted into the mass spectrometer. They are then bombarded with high moving electrons, and when the electrons bombard that compound, they knock off electrons from the atoms in this compound. Obviously, when the compound is knocked with these electrons, it's going to split into different molecules, and that's what a mass spectrometer graph will show you. But let's just go back to this question. If you're still not sure about the whole mass spectrometer thing, I will leave the link in the description box below for my tutorial where I explain this. So, in a mass spectrometer, something ions are produced. So, as I just told you, the compound is bombarded with electrons. And when it's bombarded with these electrons from the compound, from these molecules in a compound, get knocked off. So, in a mass spectrometer, positive ions are produced because when we knock off these electrons, the atoms become positive ions. When an electron, because we're knocking off electron from the compound. So in a mass spectrometer, positive ions are produced when an electron is knocked off. Okay, so a second sentence says, these ions are deflected by a something, with the something being deflected least. Okay, so the next part in the mass spectrometer is that the positive ions are being deflected and then they are detected. So first of all, they're deflected by a magnetic field. If they are being deflected by a magnetic field, that means it's all to do with the charge. So with the heaviest, it's going to be the heaviest ion being deflected least. Because if the ion is small, it's going to be straight away deflected by this magnetic field. Because magnetic fields, like magnets, they're going to be stuck together or they're going to be repelling each other, depending on which side you put them together. So, in a mass spectrometer, the smaller ions will be deflected more by this magnetic field because they're going to be smaller. And what I mean by smaller is they're going to be light. So it's obviously much easier for a light ion to be like deflected than it is for the heaviest one to be deflected. I'm sure you understand what I mean. So part B of this question says the MR of the compound is shown in the mass spectrum by. So in a mass spectrum graph, you have two very important peaks. One of them is the molecular ion peak. That's the one which is going to have the larger MZ. Let me draw you a graph. So MZ is on this axis. So the one which is going to have the largest MZ with the peak, that's going to be the molecular ion peak. There's also a different, very important peak, which can be somewhere here, and is the highest peak. The highest peak is the most common fragment. The MZ, the one with the highest MZ, is the molecular ion peak, and the molecular ion peak, as the name suggests, gives you the MR of the compound. So the MR of the compound is shown in the mass spectrum by the peak with highest MZ, and it's called the molecular ion peak. Next question says, at what MZ would you expect to see the largest value for propan-1-ol? So as I told you, the largest value, the largest MZ, is going to be the molecular ion peak, which is, as we said, is the MR of the compound. So the largest MZ will be the MR of propan-1-ol. So propan-1-ol has 3 carbons and an OH on the first carbon, and the rest of them is hydrogens. I'm not going to draw them. There are hydrogens all around. So what we got to do is find the MR. So we have 3 carbons, so 3 times 12, plus we have a oxygen, plus we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. That's the AR of carbon, that's the AR of hydrogen. Now we're just going to have to add this all up, and this gives us 60. So 60 is the MR of propan-1-ol, so that's going to be the largest value of MZ, which is the molecular ion peak. Okay, next question. What group has been lost from propan-1-ol to give a peak with a MZ 43? So we know that the MR is 60, and now we have 43. So if you take this away from this, you get 17. 17 is the MR of the part that has been lost. So you can try off different ways. You can do like a carbon plus 3 hydrogens, but that obviously gives you 12, 13, 14, 15. And then you would have to add another carbon, which is obviously way too much than 17. That should be equals. But you can also look at the other side. We have H, which is 1, and then 16 for oxygen, which gives us 17. This is the MR of OH, the alcohol part of this molecule, and it gives us 70. That's what we said it's lost. So I think we just finished. We just have to say that OH is the group that has been lost. So what you do in this type of question, you see what the MR was at the beginning, you see what you're left with, and then that's the difference. And the difference is the group that has been lost. Okay, our next question says, propene reacts with hydrogen bromide to give 2-bromopropane. Draw the mechanism for this reaction. Okay, so we are starting with propene. So our double bond, H's all around. And we want to go to 2-bromopropane. So obviously it's propane, so we're going to lose the double bond. It's going to open up, accept bromine. We also thought that it reacts with hydrogen bromide. So here's a hydrogen bromide. Bromine is slightly negative, hydrogen is slightly positive due to negativity differences. So the hydrogen gives these electrons to bromine, or bromine rather takes these electrons to itself. And now hydrogen becomes our electrophile. It wants these electrons, so it's going to get these electrons from the double bond, because double bond means that there's lots of electrons here. So it gives these electrons to hydrogen, which is electrophilic, so electron loving. The next part of our mechanism is that this hydrogen came into the compound, the double bond has opened, and now we've got this molecule going on. We are told that this is the 2-bromopropane. That means it has to be on a carbon in the middle. So we're leaving this place in the middle for the bromine, which is now minus because it got these electrons from hydrogen to come along. It goes into this positive carbon to give us 2-bromopropane. Now we have bromine here, and as you see, this is 2-bromopropane. So for this type of reaction, you look like what we start with, what you're ending up with, and then this intermediate. Explain why the product of this reaction is mainly 2-bromopropane rather than 1-bromopropane. So obviously, this hydrogen could have joined the middle carbon, and the bromine would go on the first carbon, becoming 1-bromopropane. But it much rather is doing something like this, going into the middle carbon. And the reason for this is that the second carbocation, which is this carbon, and it's called cation because it has this little plus at the beginning, is much more stable than the first and the primary carbocation. That's the reason you have to know. We could go on to why this is more stable and so on, but this is a higher level. You don't have to know this for your AS level chemistry. So I'm not going to mess around with it. So you just have to know that the second carbocation is much more stable than the first one. That's why the bromine attaches to this carbon rather than to the first one. Okay, our next question is a really long question. It's usually like a 6 marker. But we're just going to go through each of the steps. So let's just read the question first. So compound C is a compound of carbon, hydrogen, and bromine only. Bromine has 2 isotopes, 79 bromine and 81 bromine, in equal abundances. Use all the information below to deduce the structure of compound C, given your reasoning. So these are all the information we get, and we use every single one of them to get to our structure. So the first point says compound C contains 29.8% carbon, 4.2% hydrogen, and 66% bromine by mass. So they're giving us all the percentages. And what we usually do with the percentages, we find the empirical mass. So let me zoom in for you. Okay, so we have carbon, we have hydrogen, and we have bromine in the compound because it says it only has carbon, hydrogen, and bromine. So we know the percentage of bromine is 66.0%, hydrogen is 4.2%, and carbon is 29.8%. So we know this. We also know the equation N equals mass over mR. Because we're not getting the mass, but we get the percentage, we use percentage instead of mass to find the number of moles. So 29.8 over the mR of carbon, which is also the AR of carbon, which is 12. Then we have hydrogen, 4.2 over 1. And lastly, bromine, 66.0 over 80, which is the AR of bromine. So what we're finding now is the number of moles of each of them. For carbon, this is going to be 2.48. For hydrogen, this is going to be 4.2. And for bromine, it's going to be 0.825. Obviously, I've put those in the calculator. I don't know them off by head. So when finding out the empirical formula, the next step would be to divide it by the smallest number. In this instance, it's 0.825. So we divide each of them by 0.825. So it's going to be 3 for this, for carbon, 5 for hydrogen, and 1 for bromine. Obviously, I've rounded up these numbers to the whole numbers. So our empirical formula is C3H5Br. So that's what we do with the first dot. So we already used this one. We know the empirical formula of compound C. The next dot says the mass spectrum of compound C contains peaks at MZ of 15, 41, and a pair of peaks at 120 and 122. So it has peaks at 120 and 122. And we are told in a question that bromine has 2 isotopes, 79 bromine and 81 bromine. Okay, so when you look in a question, we are taught that we have the 81 bromine, and our highest peak is 122. That means that using this bromine 81, as this is the highest, this is the one with the highest MR, we're gonna get 122 for the compound with this bromine. Also, we've got peaks at 15, 41, and 120. 120 will be the peak for the whole compound because it's the second largest, but using 79 bromine. Then we've got 15 and 41. So at MZ 15, the ion could be CH3. It's a plus because they are fragments and they are positive fragments in the mass spectrum. And how do I know it's that one? Because you know, we only have carbons, hydrogens, and bromines. Bromine is obviously way too high because it's 80 for the MR. And so we left with carbons and hydrogens. And as we know, alkenes, they always go like this. So 15 is given by this part. So we already know that in this molecule, we have a part which has MZ of 15 and it looks like this, 12, 13, 14, 15. We have another MZ value of 41. So let's just count further. So 12 plus 12 is 24. When we add another 12, we've got 36, 37, 38, 39, 40, 41, 42, 43. So that tells us is way too much. So it's 41. So I'll be obviously going to get 3 carbons. So when we use 3 carbons, we know that's 36. We've got 41. So we take away the 36 and that gives us 5. So what we need is just 5 hydrogens. And this is another peak, another fragment of this molecule with empirical formula of this. So you just work through all the peaks they tell you and try to match it with appropriate atoms so that you get this number. Okay, so We know this peak, we know this peak, we know 120 is the whole molecule using 79 bromine, we know 122 is the MR of the whole molecule using 81 bromine. So I think we went through this dot already. So next bullet point is the infrared spectrum of compound C has an absorption at 550 centimeters minus 1, 1630 centimeters minus 1, and 3050 centimeters minus 1. And now you're probably wondering where they get those numbers from. So when you go on into your data booklet, you have a whole lot about infrared spectrums and all the wavelengths. So that's where you find them. So you look at the first number and you try to match it with your data booklet, and it shows you that this wavelength is according to CBr bond. This wavelength is according to C double bond C bond, and this wavelength is according to CH bond. So these are the 3 bonds that you are going to find in your molecule. So these are the 3 bonds you have to include in your structure of compound C. So that's just what the next bullet point tells us. The last bullet point tells us that the compound C is a Z isomer. Because it's a Z isomer, that means Z for same. So it's gonna have 2 groups, 2 different groups attached to carbon-carbon bond, and they're going to be on the same side of this carbon-carbon double bond. So we now have to use all this information that we've been given to come up with the structure of this molecule. So we know it has to have these carbon-carbon double bond in the middle because it's a Z isomer, and Z isomers is same as S isomers. They're gonna have this carbon-carbon double bond in the middle. We know that it has 2 groups attached to carbon-carbon bond on the same side. We also know that one of the groups is bromine, so we can already stick this in. Do you remember when I told you that 122 on the mass spectrum is the MR of the molecule using 81 bromine, and 123 is the MR of the whole molecule using 79 bromine? Look at this. The MR of bromine is 80, so I'm gonna put this into my calculator. Then the AR of carbon is 12, but we got 3 of them, so we add 36. And the last part is 5 hydrogens, so 5 times 1 is 5, and this gives us 100. Sorry, my bad. We have bromine 81, so 81 plus 36 for carbons plus 5 for hydrogens gives us 122. So this empirical formula is actually the molecular formula as well, because this gave us the MR and this matches the MR. This means that we have to use this to come up with our structure. It's going to be C3H5B R. So we already have our Br. We have 2 carbons, but we needed 1 more. So this 1 more carbon is going to be the other group that's on the same side. So we have 3 carbons, we have 1 bromine, and we've got 3 hydrogens, but we need 5. So the other 2 sides, the other side, we're going to have 2 hydrogens. This is satisfying all of these points, and that's a 6 marker. So here's the next question. We've got ethanoic acid. This is the graph for ethanoic acid of infrared spectrum of ethanoic acid. So let's just draw the ethanoic acid. It looks like this. So these are all the bonds that are going to be present on this graph. So this is an infrared spectrum. So we need to label the characteristic absorptions for 3 bonds present in ethanoic acid. So what you're going to need is your data booklet and infrared wavelengths and the bonds representing these wavelengths. And using this, you can see that you've got on your data booklet a wavelength for bond C double bond O. And it says that it's going to be somewhere around 1750. So this is going to be somewhere around here. So this one is a peak for our C double bond O bond. So next bond that we have is a carbon hydrogen. We also get a wavelength for this one on our data booklet, and it says it's going to be somewhere between 3000 and 3100. So this is going to be our CH bond. It's somewhere between 3000 and 3100. We also have got CO bond, and this is going to be our last one because we only need 3, and it's somewhere between 1000 and 1200. So I'm saying this is going to be our CO bond. So basically in these questions, what you do is you're just trying to look at your molecule and see what bonds are included on the graph. As you can see, these peaks where you have a bond look different than the rest of it because they are longer, they're wider. So that what should help you find these out. But you need a data booklet for this. You don't have to know this off by heart. Okay, the second bit says the mass spectrum of a phenolic acid is shown below. So this is a mass spectrum now. Explain how the spectrum shows that the formula of a phenolic acid is CH3COOH. Okay, so I drew the phenolic acid for you again, and we have to explain that this is the formula of a phenolic acid. So the first thing you got to do about mass spectrum is to know that the peak with the largest MZ value is going to be the molecular ion peak, so the MR of the molecule. So what we want to do is find the MR of this molecule and see if they are exactly the same. So you add the carbons together and oxygens, and you work out that the MR of this is 60. So it's exactly the same as this one. So that's the first thing that will show you that this formula is actually correct. But you also have peaks at 15 and 45. That's the two I picked. So you can use any of them, but I thought I picked these ones. So 15 is the part for CH3. 12, 13, 14, 15. So this is our fragment. So again, it shows us that this actually is the formula because this peak is present. And we also have this peak on our mass spectrum graph. The other peak that I chose is 45, and the 45 is this part, COOH, this. It gives us 45. So this again shows us that this formula is actually correct. So as I said, you can pick any peaks and try to work out, but I found these two the easiest ones because it's just the whole parts of this. And that's how you confirm. Okay, and our last couple of questions now. A phenolic acid can be formed from oxidation of ethanol. State a suitable oxidation agent and the conditions needed to carry out this oxidation. So oxidation of alcohols, you always use for the oxidation agent acidified potassium dichromate. If you don't put acidified, they may not give you a point. And our condition for this one is heat. What would be observed during the oxidation? So the main thing you're trying to find is the color change. In the color change is orange to green using this oxidation agent, acidified potassium dichromate. Okay, so the boiling temperature of ethanol is 78 degrees Celsius. Given the reason in both cases, state how you would explain the boiling temperature of the following compounds to differ from that of ethanol. Okay, so I drew these molecules out for you. so it's be easier to understand. So we know that ethanol has 78 degrees Celsius, and now we have to decide if the boiling temperature of propane, which is this one, it should be all hydrogens around. I just didn't want to draw them all around because it's going to look messy and you might not see what I exactly mean. So the boiling temperature of propane obviously is going to be lower. And the reason why it's going to be lower than that for ethanol is that ethanol has this hydrogen bond. Hydrogen bond occurs between hydrogen and oxygen, hydrogen and nitrogen, or hydrogen and fluorine. This one is the one we have in now. So the hydrogen bond is going to be much, much harder to break. And the substance is going to boil when these bonds are broken. So this bond is going to be very hard to break. So it's going to be much easier to break all these van der Waals forces in this molecule than this hydrogen bond. So this one is going to have a lower boiling temperature. The next one is butane 1-ol here, and our ethanol. Butane 1-ol. It should be on the first carbon, not the second carbon, sorry. So now they both have the hydrogen bond, but ethanol is smaller than butanol. Due to this, butanol is going to have a higher boiling temperature because they both have this hydrogen bond, but apart from this hydrogen bond, butane 1-ol will have much more, or not much more, but more van der Waals, more of the CH bonds than ethanol has. So it's going to have a higher boiling temperature. So I wrote, apart from the OH bond, which ethanol also has, butane 1-ol has more CH bonds than ethanol. Okay, so these were all the questions for this topic. I know this is a long video, but I hope it was helpful. Remember, everything I show you are my techniques and ways of learning and revising. If you have any questions about my videos, please comment or email me. I'll leave all the links in the description box below. Also, if you have any comments about the quality or content of my videos, please also leave them under this video. Like, subscribe, and see you soon. Bye!